This is Knowledge Engineering with Semantic Web Technologies. This is Lecture 2, RDF-based knowledge representations. We are still occupied with SPARQL, and in this part of the lecture we want to look deeper into more complex SPARQL queries. So let's remember what SPARQL query we did last. So you remember we had this query where we tried to find out the names of authors and the names of their notable works, and we filtered this out with only looking at the English label. So we had here used the so-called filter expression. So this was the last query that we tried to pose to a SPARQL query endpoint. So you saw here we had SPARQL operators used in the filter query, and what you can do, of course, you can combine query constraints here with logical connectives. So you can here use AND, so these are the two ampersand signs, or you can use OR to combine these patterns. And you can also use arithmetic comparison operators, so for numerical data types, for date and time, for string and for Boolean, or simple comparison like equals or does not equal for other data types. And you can use arithmetic operators, of course, for numeric data types like plus, minus, multiplication or division. And in addition to these, let's say, simple operators, you also have the possibility to do operation on strings, on character strings. And there you have the possibility to do string matching based on regular expressions. For this, you should have a look at regular expressions, how they work. Maybe you know them already. And they can be applied here within the regex directive of the filter expression in a SPARQL query. Moreover, you have also the possibility to distinguish or to decide whether two terms or two variables really have the same content with same term, and you can decide whether two variables contain expressions or literals within the same language, so have the same language tag, and this would be lang matches. So these are more expressions or filter functions that you can use. So let's have a look how they are applied within an example. So this is again our old example looking for authors and their notable works, and of course we are filtering already for only English labels. But the new thing here is we also want to find out only titles that contain the word love. So how do we do that? So we use another filter expression, and here we simply try to filter out all the titles which contain a specific string. So this is given as a regular expression. So it means here in this regular expression, first I specify the variable of the literal that I'm going to analyze with a regular expression. Then in quotation marks comes the regular expression itself. I simply look for the pattern love. That must be somewhere in the title variable. And then I have several flags that I can use, and I use the I flag, which stands for case insensitive, which means I do not care whether love is written in capital letters or in lower case letters. So let's try out this at the SPARQL endpoint. So you know this already, this link leads us directly to the SPARQL endpoint where we see the very same query. And I run the query, and you see here as a result we only have titles here of books and authors who have written these books that contain the name love. So let's have a look. So what we have here, yeah, for example, Elizabeth Gilbert, yeah, very famous author, Eat, Pray, Love, maybe you know that. So of course this contains love. Or D.H. Lawrence, Lady Chatterley's lover, so there is also love in the title. Okay, you see, this works quite well. So if you want to know more about regular expressions, simply follow the link we have given here, and you can learn more what kind of patterns you might ask here and how you can use this sophisticated function for further filtering the SPARQL query responses. Okay, so when the filter constraints are evaluated, you of course have the possibility to apply operators. We saw that. But you have to take into account that you do not work with the so-called usual binary logic. You are working here with a three-valued logic, because the result of the filter cannot only be true or false, it can also result in an error. So, and here are simply the truth tables that are used for this three-valued logic. If, for example, in an AND or an OR operation or in a NOT operation, the result error also occurs. So what you see here in the first truth table, you have the values true and false in the first 4 rows. So everything in the first 4 rows is like it always is in binary logic, but then row number 5, there we have at first the expression E, which denotes error. And if you denote true and error and want to combine this in a disjunction, so via logical OR, this results in true. And if you combine it via AND, it results in error. Otherwise, if you combine the false value with error via the logical OR, it does not result in false, it results in error. And if you combine it with AND, it results in false. So, and it's the same here if you look at the complement. Of course, true and false are the complement of each other, and the complement of error here is also error. So these are the truth tables for the three-valued logic that will be applied when filter constraints in SPARQL are evaluated. Because for some constraints, maybe they result in an error because, for example, you try to apply a numerical operator on a string or a numerical operator on a date or a URI, which is not possible. Then, of course, this filter expression results in an error. And maybe it is combined with another expression, and then the evaluation is handled according to these given truth tables. Okay, so let's go on. What else can I do? So we had filter expressions, but we know sometimes maybe we want to have results that are a little bit more, let's say, that are a little bit more complete. So we know that the single lines within the basic graph pattern, so the single graph patterns usually in the SPARQL query are combined conjunctively. So this means, for example, if I want to have for all the books in my query not only the English title but also the German title, I will only have as a result authors and titles of books which have both the German and the English title. I will not have books in my result that only have the English title but do not have a German title. So if I want to combine German and English titles with a logical OR, this is with a usual graph pattern not possible. For this we need an additional keyword. There we have the optional keyword. And the optional keyword simply combines this query in the sense of SQL in the relational databases like a left outer join. So maybe you know that operation. So optional simply means I apply an additional graph pattern or triple pattern, but only if it's really applicable. Nevertheless, I will return the result also if this pattern does not really return a result. So here in the query, we filter for books that have a German and an English title, but we want also to return books that only have an English title. So the German title only is optional. So let's try that out. So you see that here we have the optional keyword. Here you have to keep in mind everything or all patterns that are optional have again be written into another pair of curly braces. And here, for example, I say, okay, I also want to select a title. Here I distinguish between English title and German title, and in the optional case here I have the German title, which is here DE title, and here I filter for the language tag DE for German. And of course, to have this in the result, I have to take care here also in the output variables that I do not have only the author name, the English title, but also the German title. So let's try it out. So here we have again the SPARQL endpoint with a query. And I run the query, and you see in the result here I have a column for the author name, a column for the English title, and I have a column for the German title. And if we scroll down a little bit further, we will see here are books that do only have an English title but do not have a German title. So this you achieve by using the keyword optional. Okay, so this was an optional query filter that you can also, or an optional query pattern that you can apply. Besides the conjunctive connection, we also have the possibility to make a disjunctive connection among certain graph patterns. So you combine two graph patterns via a union here. So this is a logical OR in that sense. So what we want to do here in this example is we want to retrieve all influences of Jules Verne and all the people who Jules Verne has influenced. So these are two different graph patterns. So in the first one, we want to have Jules Verne has influenced certain people, and in the second one, we want to have Jules Verne has been influenced by several people. And both of them should be then, of course, in the result as output variable, as you see here. And if I combine both patterns conjunctively, you will possibly end up in no result, because then influencer and influenced possibly should be the same. So here you should definitely combine both with a union to make a combined result of both. So this is a logical disjunction. So either this one has influenced Jules Verne, or this is somebody who was influenced or who has influenced Jules Verne. So we try out the query again. So you see here the SPARQL endpoint, and I run the query. So what we see here, of course, first are people who are influenced by Jules Verne. So for example, Arthur Conan Doyle or H.G. Wells are authors, or J.R.R. Tolkien, for example, are authors that have been influenced by Jules Verne. And on the other hand, also Jules Verne has influences. You see them here. So these are some of the French authors like Alexandre Dumas or Victor Hugo, but also he was influenced by Daniel Defoe and Edgar Allan Poe. So this is an interesting result, and they are both combined via OR or union. So this is the SPARQL union directive. So with union, you are able to make a logical disjunction among graph patterns. Okay, so what else is missing? So we also have the possibility in SPARQL of negation. So for example, when we look at our old example where we have looked for authors who have a notable work, there also might be authors in DBpedia that don't have a notable work. So how to query that? So you have several possibilities to do this in SPARQL. The first possibility simply would be look for authors where this variable work is not bound or cannot be found. So this works in the following way. So what I want to do here is I want to select authors. And of course, these authors should be writers. And then I say, okay, select also the work of these authors, but I put this here again in optional because, again, I do want to have authors that do not have a notable work. And I filter this in the sense that I say the variable work here, the object of that triple pattern, should not be bound, which means I want to look for authors who do not have a notable work. And the result will in the end be the following. So here you see a list simply of authors that do not have a notable work. So possibly you might find a familiar name. So there are lots of authors who do not have a notable work in DBpedia. So this is rather complicated. And the new SPARQL 1.1 also has other possibilities. This stems from SPARQL 1.0, so from the old version. You also have a more simpler possibility because now in SPARQL there also is a filter option which is simply called not exist. So what you can do here, for example, is you can select an author and then you specify again, okay, this author should be of type writer. And then you have a filter option, and the filter option here is not exist, and you say exactly this triple has notable work, should not exist. and it will deliver exactly the same result as the not bound version. So this is a much simpler version to do that. Moreover, to make things more complicated, there is even a third possibility which works with the minus directive. The minus directive is a little bit different because usually it subtracts graph pattern from the result. So what you do here is, again, you select authors, so who are writers, but you do not want to have authors who have a notable work. So you select all authors, and then from all authors, you subtract a graph that contains authors who have a notable work. So it's the other way around. So for some possibilities, for the simple possibility, it's the same, but for some possibilities, it depends. So if you have complicated graph patterns, the minus changes the graph pattern, and the query result is dependent on the position of the minus. So from which partly or from which subgraph that you specify, you subtract then the pattern. So this again can be a little bit complicated, and you can play around with it. So you should take care with minus is more complicated, and there of course the position is really important. For the other things, it's more simple, it's easier, straightforward if you are working with not exist. So these are the possibilities of negation within a SPARQL query. So up to now, we have only worked in a single SPARQL graph, in a single RDF graph that we have usually defined in the from clause of the SPARQL query. It's possible, of course, to query several graphs on one SPARQL endpoint. So here, therefore, we decide between the default graph where the query is working, and then we can specify several so-called named graphs that we can then explicitly address within our query. If you want to address a named graph, you simply specify this graph within the where clause with the graph keyword or graph directive, where you specify exactly a new graph, which is given by a URI of the graph, and then in curly braces, you state your query or your query pattern that you query to this named graph. So in the end, you can combine default graphs and named graphs in rather complicated ways. For example, like this one here you see on the right-hand side, a more complex query where you first have two default graphs. So you have two from clauses, which is HPIG1 and HPIG4. These are the graphs that are or that form our default graph. And then you specify three named graphs. So you have also the possibility to specify the named graphs here beforehand. You say first named graph you ask is HPIG1, second named graph you ask is HPIG2, and then HPIG3. And then in the work clause, of course, again, you must specify which graph to query. If you don't specify any graph, so like the first query, or the first triple pattern, which is A, this refers always to the default graph, which here again consists or may consist of two separate graphs. And then you specify graph HPIG3, for example, which refers to this specific graph. And then you also have the possibility, you see this query really subsumes everything which is there. So you also have the possibility to specify a graph and do not explicitly address one graph, but use a variable which addresses then all graphs, or which is restricted somehow to be constrained to several graphs. So here you can address all the named graphs here with the variable G, and then the graph pattern C is addressing the three named graphs you have here. So these are aggregated all possibilities to query several graphs and named graphs within one SPARQL query. But keep in mind, these graphs all are on the same SPARQL endpoint. So this is not a possibility to ask or query several SPARQL endpoints. This is not a federated query. This is simply a query which combines different graphs. Okay, now you might ask, so from where do I know which graphs are available? This is quite easy. So you can address a SPARQL endpoint and can simply here use the graph directive and can ask here for the available graphs that provide any kind of pattern. So I specify here a graph pattern that contains three variables, and I'm asking for all available graphs here. So I say select distinct, all distinct graphs that provide some kind of triple pattern. So let's try this again on the DBpedia SPARQL endpoint. So you see here, it's exactly that query. And I run the query. And you see here, these are the URIs of all the available SPARQL endpoints, all the available graphs, sorry, on that single SPARQL endpoint. And here is the one, for example, for the DBpedia, and it's dbpedia.org/SPARQL. So this is one of the graphs that can be used here. And of course, there is also the usual DBpedia org that we are using. Okay. So these are DBpedia graphs. So graphs rely usually on the same endpoint, and if you are trying to address several endpoints, these are so-called federated queries. So there the results of several SPARQL endpoints can be combined. For this, there is another keyword or directive which is called the service objective. And with this keyword service, within the work clause, you can specify another SPARQL endpoint. So here, for example, we are addressing in this example the linked movie database. This is given in red, and the DBpedia, which is given in blue. And in the red part of the where clause, we see that we are using the service linked MDB. And there the SPARQL endpoint, we are asking for movies, and we are filtering for movies that have a connection to DBpedia there, that have a same as connection to some URI that is in DBpedia available. And then in the blue one, we are asking DBpedia for all movies, or we are trying to find which is the subject of this movie. So here, two SPARQL endpoints are combined, but the problem is if you try to pose exactly that query to the DBpedia SPARQL endpoint, it won't allow you to do federated queries. Of course, public available SPARQL endpoints are rather restrictive about asking other SPARQL endpoints, because you could use this simply to initiate a denial of service attack or stuff like that. So what you have to do usually here is you have to install your own SPARQL endpoint. This is quite simple, so we will give you in the material to that lecture also the link to very primitive and simple SPARQL endpoint, for example, the Fuseki server. And there you have the possibility on your own desktop or on your own computer to install a SPARQL server and then also to try out these kind of federated SPARQL queries. Okay. So we have learned a lot of more complex SPARQL queries, and in the next part of the lecture, we will have a look at so-called aggregation functions and at property paths.